Yes. Hello, everyone. Today we have with us Dharmaraj Ramachandran with us. He is a PhD scholar at BITS Pilani Goa campus, and his research interest is in quantum information and machine learning. And today we all know what's the topic of our talk is. It's on robust entanglement measure for mixed quantum state, which is based on his one of the archive papers he has. So let's enjoy the talk. Let's have lots of questions, and the participants can ask you question in between, right, Dhanraj? Yeah. So you can ask him questions anytime if you find any difficulty in understanding anything. So from here on, the floor is all yours. The meeting is all yours. You may start presenting.
Yeah. Thank you, Shreya, for the kind introduction and for the invite too. So, like you said, this talk is going to be a theoretical talk about an entanglement measure which we cooked up. So, yeah, I'll just share the screen. And mm, yeah, just confirm once if the screen is visible.
It is visible, although you may need to like zoom in a bit.
Zoom in a bit. Yeah, that's right. Okay, I'll use. I think this share screen went off.
Yeah.
Yeah, right. So I'll do something. I'll share the entire screen and try that. Now is it full screen?
Yeah, it's much better.
Yeah. Let me try this also. Now I think it should be full.
Yes.
Yeah. Okay. So welcome everyone. So this talk is about robust entanglement measure for mixed states. So this talk is completely and entirely based on an archive submission that we did last month. So for people who are strong enough to read it through by themselves, I think this talk is just practically a waste of time. So I'm just going to explain that paper in a detail and the motivations behind writing some stuffs there. So my name is Dharmaraj Ramachandran, and I'm from BITS Pilani Goa campus, and I'm a PhD. And yeah, this work was done in collaboration with two of our project students who work very sincerely, Aditya and Subramaniam, and of course my supervisor, Dr. Radhika Vatsan. Yep. So the talk will be scheduled, or the order will be like this. It's still an half talk, so stop me anywhere wherever you don't understand something or wherever I jump between topics. So this talk is arranged like this. So first, I will try to motivate you how serious entanglement is and why we should definitely measure it. And then I will tell you one entanglement measure that's very famous and very well known. And of course, I'll try to highlight what are its drawbacks. There are two drawbacks that we find or the community knows about the entanglement measure. And then we introduce our entanglement measure. The point of finding a drawback in somewhere is to invent something new. So we introduce our entanglement measure here in the third point, which we call as MBN, Modified Bloch Norm. And once we introduce that, I will again address the two drawbacks. I'll go back to the two drawbacks and I will see if this measure is of any good for those drawbacks. Is it performing at least a little better in some cases? And turns out it does. Like advantage 1 and 2 shows that those two are the two major results of this letter. So where I show improved discriminants and robustness, the two advantages that it has than the existing measures. And then we summarize the talk. So yeah, so most of us who are here would have heard, even people outside the community would have heard the word entanglement, and we all know it's a very fundamental resource in various quantum information protocols like teleportation or superdense coding or various other algorithms. So when I mean resource has a very proper and perfect definition in the community, in the literature. So in a very simple sense, what does resource mean is, if you have a particular quantum information task, say teleportation, and you, to accomplish that task, you definitely need a quantum state that is entangled. Then entanglement there is a resource. So if you cannot accomplish a particular quantum information task without a particular property of a state, that property turns out to become a resource. And entanglement is a resource in various protocols. In so many famous algorithms that we know of, entanglement is a resource. So once we understand that entanglement is a resource, the other natural instinct, it's not just for information theory. Everywhere we measure resources, right? So we measure, if we say water is a resource, we measure it in liters. If we say electricity or energy is a resource, we measure it in joules. Or rotation is a resource, we measure it in RPM. So like these measuring tools, like we have measuring tools to measure the amount of resources. Why we do that? Because say for example, if I say that I'm sending you water, but I don't tell you whether I am sending you nanoliters of water or gallons of water, then you won't be prepared to receive it. And so entanglement being a resource, it will be distributed, sent, shared, generated, destructed all around networks and all around the place. So in that case, we have to know how much we are generating, or how much we are utilizing, or how much we are sending. So in various aspects, the need for measuring entanglement is quintessential in quantum information theory. So, with that justification for measuring entanglement, let us define it. So, in a very proper sense, entanglement of a pure state is defined that if a bipartite state could never be written as tensor product of two single partite states or partite states, then it is said to be entangled if the state is a pure state. In the case of a mixed state, so most of this talk is focused on mixed states. So in the case of a mixed states, apart from even mixtures of such product states are said to be separable. So any state that could not be written as mixture. So here pi is a probability, which means that you're classically mixing product states. So even states that are classically mixed product states are still product states. So mixing is not going to give you entanglement, is what the definition says. So any states that cannot be written in this form is going to be a entangled state. So, apart from all the technological advances and all the huge, huge technology that's running behind quantum these days, entanglement is a very fundamental property of quantum physics, and it has amused so many physicists throughout the day, from the day it has been coined or it has been into the literature. So, apart from its technological requirements to measure entanglement, measuring or studying entanglement could have direct consequences in fundamental physics itself, could enhance our understanding in physics or how things work itself. So having said that, let us see about how do we go about in measuring entanglement. So negativity is the most famous entanglement measure, which is used to measure entanglement in the literature. And negativity is built on a separability criteria. So there is a criteria, and negativity is built on that. The criteria is known as positive partial transpose criteria. It's very famous. I think it's roughly 20 to 30 years old by now, 30 years old by now, and it's extremely strong. So what the criteria says is, if you have a density operator and you do an operation like this, you do a partial transpose, that is transpose only a subsystem of the density operator, and then you get a partially transposed density operator rho TB, which is partially transposed only in the B bipartition. And then you find the eigenvalues. We know that before doing this operation, the eigenvalues are going to be positive semi-definite. That's either 0 or above 0. But after you do the partial transpose, the eigenvalues, if the eigenvalues are greater than 0, still remain greater than 0, then the state rho is said to be separable. And if the eigenvalues are lesser than 0, people said, then yeah, then that's a signature of entanglement, right? Because the criteria just says if it's greater than 0, it's separable. So lesser than 0 could be a signature of entanglement, right? So basically, the violation to the criteria is how the measure was built. So there is a PPT criteria, and then its violation, which is called as negativity. The name comes from the meaning that all the negative eigenvalues of the partially transposed density operator is summed up. Practically that. You just do the partial transpose and you find the eigenvalues, and whichever ones are negative, you just add them up. And of course, there are some scalings and there are two, three definitions, and but in its heart, negativity is just this. You find negative eigenvalues and you add them. So if there are the amount of negative eigenvalues is more, than you have higher amount of entanglement, is what negativity says. This is the most used and most common measure to measure the entanglement of mixed quantum states even in higher dimensional systems. But having said that, having been so much used and being very strong, it still has drawbacks. And one very well known drawback is there are entangled states which have zero negativity. So it's like saying that there is water in, I mean, there is mass in an object, but the weighing scale that you invented, your scale, your measuring scale, doesn't detect the mass. It just says zero mass. So it's practically like that. So negativity says that a state is, even when negativity says a state has zero entanglement, the state could have entanglement inside. Such states are called as PPT entangled states because they are positive partial transpose entangled states, or also bound entangled states. So I'll be frequently using the term bound entangled states to refer the states which are not picked by negativity but still have non-zero entanglement. And now, okay, there are some states that negativity misses because the PPT criteria is not a completely necessary and a sufficient condition. Okay, so it misses. So what's the big deal? Is it really a big problem? Turns out it is, because there are quantum information processing protocols. There are various protocols that could be completed with bound entangled states. So bound entangled states are as good as a resource as any other entangled state in various protocols. So it's not like they are useless states which nobody wants to measure. They are useful states. They are useful in protocols. That's why we had the idea of measuring entanglement. So they are useful states. So we would like to measure them. So that is the first drawback. And the second drawback is sort of not theoretical. It's it is theoretical. It is not hardcore theory. It is based on the fact that we cannot always have a precise density operator. So this fact is commonly overlooked by theorists, but still. So we cannot always, we can never estimate the density, or I mean, we can never exactly calculate the density matrix of a quantum system for reasons that I will again elaborate in a later slide. But for now, bear with me, accept this fact that you can never have an exact density matrix. But negativity is built on a density matrix. So because of that, um, it's not always very easy to calculate negativity of a density operator. So these are the research gaps. So in this work, we try to address these by defining a new measure. That's the entire motivation behind this letter. So once we know that we are going to build an entanglement measure, the path we chose, it's not necessary we have to choose this path, but the path we chose is to look for other separability criteria, because we felt the separability criteria is where at least the first problem arises. The weak discriminants problem arises because of PPT. So let us look for other criteria. Then we have other criteria which are very well known and very well defined. I have listed three of them. There are more in literature: realignment, CCNR, and improved block matrix criteria, which is the IBM criteria. So in this work, we built an entanglement measure which is based on the IBM criteria. So the IBM criteria was, I think, defined in 2016 in the literature. So we take that criteria to build our entanglement measure. So the motivation behind choosing this criteria is sort of the bias the authors of this papers had with physics. So we are all physicists by training, and IBM criteria, once I define it, you'll see that it's very close to what you see in experiments. So it was very relevant to experimental observables that you see, and that's one reason. And the second reason, it's not a single criterion, rather it's a family of criterion, so it's a criteria in that sense. So it's flexible. You can you have some parameters which you can tweak, alternate to improve it in certain scenarios. So because of these two reasons, we chose to build an entanglement measure which is based on the IBM criteria. And so how do you do, what is IBM criteria? So in the next two slides I will try to explain how IBM criteria was built. So this was very interesting work. So block matrix, the idea of block matrix has been there for a long time. So block matrix, for people who are not introduced to it, it's just another way of writing a density matrix, in the sense that all the information in the density matrix could be recasted into a different matrix called as a block matrix. The block matrix is basically this B row AB, which is written here. R and S are one-dimensional vectors, so they are long, and T is a matrix. So how are the entries of B found? So you just find the expectation values with respect to lambda I and lambda j tilde, where lambdas are basically a complete set of traceless orthogonal Hermitian operators in HA and HB. So I think it's not a very big crime to assume that they are generalizations of polymatrices. So in some sense, if we have an intuition about how polymatrices span the entire space of single qubit space, we know how the single qubit block ball or block sphere works, then these lambdas are like generalizations of them which obey the same properties that polymatrices do. And it's like a basis. They form the complete basis, so that you can define any density matrix using these. So the expectation values found with respect to these tensor product of these generalized polymatrices or generators are going to be the entries of Bij. And as you can see, why are R and S important? Because R would be like the entries. So if you see the indexes in a little bit detail, your when your I is 0, it's basically the identity matrix. We have ordered it that way. So when your I is 0, it's basically the identity matrix. So R and S are like the local expectation values of the subsystems, and T would be like the correlation part of the matrix. So in the block matrix, there is a very nice way in which the local information and the correlated information splits out, which never happens in a density matrix. So for a physicist, this lit up our eyes. So we have a matrix representation where visually the places where numbers are put are tell us how the system is correlated. So R and S are like the local block vectors, and T is like the correlation part of the matrix, and the overall matrix is called the block matrix. So that's how we build a block matrix. Once we build a block matrix, we have to modify it. So that's the final step. So block matrix has been there, but in 2016, I think, yeah, 2016 scientific reports, Shen et al. So Shen et al. And various other Shen and his colleagues have defined a way in which you could modify this block matrix in order to give a an improved separability criteria. So how do you modify? So let us take an example where we do a one-step modification. That is, when m equal to 2, the 1 here becomes a 2 cross 2 matrix of ones. So this becomes 1 1 1 1. And since that has become 1 1 1 1, R has to be padded up as R and R, and you scale the entire R with a number called A, and you scale the S transpose with a number called B, and you pad S and S transpose here. So as you can see, the modified block matrix is bigger in size, but the T is just kept in the same shape. So this is how you modify a block matrix. Here m can be any positive integer and b can be any real number. By which what I mean is, you could set m equal to 100, and this 2 cross 2 matrix would become a 100 cross 100 matrix, and you will have 100 copies of R and 100 copies of S. So basically, whatever the information was present inside the block matrix is still only there in the modified block matrix, but it's just I would say, a linear algebra game where you have padded up the information multiple number of times to improvise on your separability criteria. So what's your criteria? when you find when you find the norm of the modified Bloch matrix, its norm for separable states, if the norm is lesser than a particular number, the guy on the right side is basically a number. So if the norm is lesser than this number, the criteria qualifies that state as a separable state. So here m could be any positive integer, like I said, and a is any real number, and the capital N and capital M are the dimensions of subsystem A and subsystem B. So yeah, this is again just a number, and if the norm, if the trace norm of this modified Bloch matrix is lesser than a particular number, we have a separable state, is what the criteria says. So so what did we do? So this is all what that was there in literature. Then we did a very inspired step, I would say, from what we saw in negativity. Negativity had a PPT criteria and its violation was negativity. So we thought, let us define an entanglement measure which is based on violation to this criteria. So MBN quantifies a violation to the IBM criteria. So the violation is basically the trace norm of a given density matrix. If you have a density matrix rho, you find its trace norm, and you basically find its difference from C, where C is this number, this big number here. So you find its difference from C, and that difference is your violation. And if that violation is a no, is a number that's more than 0, then you have entanglement. That's basically MBN. So if you want to see it pictorically, if this is your criteria, and the yellow part is separable states and the green part is your entangled states based on the criteria, it's not a strict line, it's based on the criteria, and your row is somewhere here, then how much your row is far away from this line, that is what we are practically quantifying. And the division is basically a normalizing factor, because we want entanglement measures to go from 0 to 1. So we want maximally entangled states to have entanglement 1. So to normalize the measure, you divide it by violation by the maximally entangled state. So then you have MBN. So MBN is defined in this way based on the improved Bloch matrix criteria. So to recall what we have discussed, we had we discussed why we need to measure entanglement, and we discussed the problems with the existing entanglement measure, which is negativity, one of which is weak discriminants. And now we have built a new measure which is based on not on PPT but on a different separability criteria. Now, before jumping into results, we must definitely make sure if this is a valid entanglement measure. And entanglement measure is nothing but a function of a density matrix, a bipartite density matrix in this case. In all discussions, I'm just talking about bipartite entanglement. So that number should be between 0 and 1 for it being nice. So if it's going to 0 to 10,000, it's going to be very odd, and you cannot compare it with other measures. So it's nice to range it from 0 to 1. And what are the properties it should have? It should be monotonic, convex, and discriminant. There are more properties, but they are additional requirements. These are fundamental requirements. So monotonicity is basically saying that there are operations in information theory which are local operations in classical communications. And monotonicity basically says when you do these operations, the entanglement predicted by the entanglement measure should not increase, because these operations cannot create entangled states. So even when these operations are done probabilistically, so sometimes they are called stochastic local operations in classical communications, commonly known as SLOC in the community. So under SLOCC operations, the entanglement measure should not increase. And convexity, basically, like if you look into it, it's just mixture of two density operators giving a particular lesser than a particular number. Why is that? Because like we discussed before, mixing cannot increase entanglement. So convexity just says if you mix two density operators, their entanglement, the amount of entanglement predicted by the measure should not increase. So that is ensured if the measure is convex. And discriminants is sort of intuitive rather than mathematical. Discriminants, there are two kinds of discriminants: the stronger one and the weaker one. Stronger one says the entanglement measure is 0 if and only if the state rho is separable. But weaker discriminant says, okay, chalo, like you can have zero even if the state is entangled, but it should be zero definitely if the state is separable. So E of rho is zero if rho is separable. So that's weak discriminants. So where does MBN stand? We have shown in the manuscript, which I'm not showing the details here, but MBN is monotonic, convex, and weakly discriminant. So I mean, some people this might be a little upsetting, because we had the problem of discriminants with negativity. We built a new measure, and then again we have just weak discriminants. We have not escaped the weak discriminants, because negativity also had the same problem. It was zero for entangled states, which we called as bound entangled states. But now MBN is also zero for some entangled states. It's just weakly discriminant. To, I mean, console ourselves with this problem, the fact is that no entanglement measure can be strongly discriminant. So that's like end of the story. This result has been proven and is very well known in the literature. It's known as the quantum separability problem. Given a bipartite quantum state rho, can we tell whether it's entangled or separable? It's a simple straightforward question, but there is no straightforward answer. In general, the answer is no. For a general mixed quantum state of finite dimensions, there is no criteria that you can invent that will tell you whether it's perfect, that will perfectly tell you whether it's entangled or separable. The consolation is, for pure states we can tell if the state is pure, we can tell. Of course, we all might have heard of Schmidt decomposition or various other criteria with which you can tell if the state is entangled or not. For mixed states, if the subsystems are of smaller dimensions, 2 and 3, then yeah, or lesser than that, then we can definitely say using PPT criteria. That's why PPT was very celebrated, because it was perfect in smaller dimensions. But for a subset of general mixed states, all these criteria work, like PPT, CCNR, realignment, IBM. All criteria work only for a subset of general mixed states. So PPT is not an exception, and IBM is also not an exception. But IBM can pick in entangled states that were never picked by PPT. Basically, IBM can detect bound entangled states. That was why that paper was written in 2016. People wrote that because they realized that they can detect various bound entangled states using IBM. So yeah, you can maybe look up into this if you are still worried why we cannot have a strongly discriminant entanglement measure. It's basically like it's almost proven that it's an NP hard problem. And having said all this, now we are in a position to see what can MBN do, what can modified block norm actually do. We have three interesting results to begin with. One is, two of them are based on improved entanglement sudden death time. Sorry, I didn't abbreviate this. So, improved entanglement sudden death time. So, entanglement sudden death is a phenomenon where entanglement dies in a finite amount of time. So, when people are building networks or building circuits, they would this is the standard metric that one would calculate to know until when they can do a particular protocol, because once entanglement is died, you're not going to be able to finish a protocol. So ESD time is like sort of telling till how long can I use this vehicle, sort of, in analogically. So MBN helps you to estimate ESD time in a much better way. For example, we have a state rho alpha, which is a 2q-trig state. It's a very lengthy to write it down. It's a very lengthy state. For people who are interested, they can look up into this reference, or maybe go back to the archive version of this manuscript where the state is written out. So for time being, just accept that there is a 2q-trig state, which for which is which is parameterized by alpha, and we are setting alpha to 4.5, and it's being mixed with a maximally mixed state. This is known as the depolarizing noise. So when it's undergoing depolarizing noise, negativity says entanglement dies around somewhere 0.1, but actually it doesn't. The state has non-zero entanglement, and it dies much later, around somewhere in between 0.2 to 0.3. So this time interval could mean a lot with in computation or in networkings where it makes sense, where you have predicted entanglement sudden death time in a much better way than what you could do with negativity. And this state again is not is a very, I mean, Horadicky, when they wrote this manuscript, they promised this state is useful in teleportation. So we have considered states which are useful, I mean, which are useful in certain protocols. So similarly, we have took another state which was shown in 2018 to be useful in meteorological purposes. It's a 4-qubit state. It's a 4-qubit state, and we subjected it to dephasing noise. This state by itself is a bound entangled state, so it cannot be detected by negativity. Negativity for this state at all times is practically zero. But when the state undergoes dephasing noise with a dephasing parameter of 2 seconds, we can see that entanglement survives for almost zero point 0.1 seconds, which is a long time. Um, when you consider gate pulse times for trapped ion systems, the gate pulse times are all of the order of microseconds. So here, entanglement survives for almost zero point 0.1 seconds. So you can do various gate operations within that given time, which you could not study with negativity, but you could if you have MBN. And third result in this particular subtopic is freezing of bound entanglement. So this freezing has been shown for some other distillable entangled states in literature. So where freezing is nothing, it's just literally freezing. Entanglement after some time decreases and just freezes in particular value. Throughout the dynamics, it just remains the same. So in this work, we took a state called rho BD, which is again shown to be very useful for experimental preparations. So it's easily preparable state, and also to measure, of course. So you can look up to this reference to see how beautiful the state is. So when this state is subjected to correlated amplitude damping noise, whose similarity is given here, A is annihilation operators. So when it's subjected to correlated amplitude damping noise, its entanglement reduces and freezes at a particular value. Again, this state is bound entangled state, so it cannot be detected by negativity. Negativity cannot show this freezing; it just shows zero at all times. So actually, it never goes to zero. That's the point. So um, the interesting dynamics that we are able to see, we could never see if we just had negativity. So these are the three examples where using a different criteria than PPT would come to the rescue to see interesting dynamics and rich features of entanglement, which one could never observe if we just had negativity. So this is all about the first subtopic about weak discriminants. And from here, I will just shift gears and jump to the next problem that I said. So when I addressed two problems with negativity, one of which was weak discriminants, and we can see that we have a measure that could detect states and show dynamics of states, which was never shown by PBT criteria or negativity. And now we will jump to another problem with negativity, which is the requirement of an exact density operator. So we would like to coin a word here called robustness. It's not mathematically defined. It's just, I would say, a feel, basically a feature of an entanglement measure to withstand errors in state estimation. So when you estimate a particular quantum state, and that error is thrown into the entanglement measure, because entanglement measure is going to have that error inside. How much does it absorb, or how much does it give back? Like how faulty it can become if the state itself has an error. So to just make this complete, why do we even estimate density operators? Is it just a, what do you say, technological challenge? Or maybe we would get rid of it in 2 3 years. Why are you even worrying about it? No, it's not that. Because density operators could never be exactly calculated in reality for these two reasons. Observables needed to characterize an n-level system scales exponentially. So it scales as n squared minus 1. So if you have, say, 99 qubits and 100 qubits, the scaling is 99 squared to 100 squared, which is large. So the number of observables that you have to measure in order to reconstruct a density operator scales vastly, and it's going to be practically impossible after some time to get to measure all those observables with extraordinary precision. And the second more fundamental problem in entire quantum mechanics is density operators are practically listing of probabilities in a particular fashion, right? So probabilities are found out only when you do infinite measurements. So you need infinite copies to know a probability exactly. Say I say that there is 1/6 chance of a dice giving a particular number. The only way for me to know it without actually knowing the properties of the dice is to measure it infinite times to say that probability is this much. Until I measure it infinite times, the probability that I have is limited to the sample size. So always you have a finite sample of finite copies of a state from which only you estimate a density operator. So you can never have infinite copies. So always the density. So all this I'm saying because density operators is could be will be always faulty. So what are the estimation techniques we have? The common estimation, there are four common estimation techniques. Two of them are maximum likelihood estimation and Bayesian inference. Both are very strong and very commonly used also. But the problem with them is they are computationally very intensive. They are very expensive operations, and in certain cases it might take months or years to finish a particular computation. So even though they are very nice techniques, they are computationally intensive. But still they are used. Of course, people with the facilities or for smaller systems, people still prefer mles and bi. And machine learning these days have come into the picture, and there are pretty impressive works that talk about machine learning's application in quantum state tomography. But it's still under research. It's not like a general problem is solved, but people are trying to address bits and pieces of it, and the progress is very good. Then we have linear inversion. Linear inversion, on the other hand, is very simple, extremely trivial. Anybody could do it on their laptop, but it generates negative Hermitian matrices. So, by definition, quantum states are positive semi-definite. So they cannot have negative eigenvalues. But quantum states that are estimated using linear inversion could be negative. So that is the biggest problem with linear inversion. But still, because of its computational advantage, we would try to address how robust these measures are with linear inversion. That's going to be the plan basically. So a study of for something like robustness, I won't say exactly robustness, but something like robustness for various entanglement witness was performed last year. It's a very nice work done by Pavel and his colleagues. So people who are interested about topics like this, where entanglement certification is done for practical purposes, please look into this particular paper. And in this work, what we have done, we have taken one step further. Here they have studied entanglement witness, but here in this work we study the robustness of negativity and MBN when the density matrices are estimated using linear inversion. So when the density matrix is estimated using linear inversion, saying that they could possibly have negative eigenvalues, how well negativity and MBM perform? Do they have the same amount of error, or is the error different for both of them? For simplicity and for without any loss of generality, to be precise, without any loss of generality, we have considered maximally entangled states and random LU equivalent maximally entangled states. So we have estimated the entanglement of maximally entangled states in different dimensions, which are LU equivalent. In the sense, we have locally unitarily rotated them so that there is no bias on the sparsity of the matrix or so on. So what is linear inversion? Because we are going to be using it. Linear inversion is very trivial. We all know that any density matrix could be written as identity plus the basis traceless Hermitian matrices, which are sigma i's here. So again, you could there is no harm in assuming sigma i's are generalized poly like matrices, and in the block sphere picture, these are just poly matrices, and xi is our estimated expectation value. The exact expectation value would be the one that you get after infinite measurements, but xi in this case would be the incorrect expectation values that you get using finite copies. So that inaccuracy in xi creeps into row estimated. And row estimated, yes, it is ensured that it's always Hermitian. That's ensured by linear algebra, thanks to it. But it can have negative eigenvalues. That's the pinch of salt that we have with us. Having said that, how, let's see the results. How well does it behave? So for the 2-qubit cases, when we have 100 copies of a state to perform to measure the expectation values, the error rates are practically the same. Orange one is negativity and blue one is MBN, and we can see the error rates are practically the same. The y-axis is basically the counts, so error rates are practically the same. There is not much advantage, and this is what one would typically expect. But when you go to 3 qubits, where we have used 700, so this small n basically says the number of copies of a state we have used. So as I said, the sample size is finite. We have used only 700 copies of a state, and then we try to estimate MBN and negativity. We see a very nice difference that negativity has a error that is much higher statistically than MBN. And as you go to 4 qubits with this much number of copies, the difference is very clearly visible. MBN has much lower error, so this error is practically tolerable. It's only centered around 0.2 and it's between 0.3, but negativity has a huge error. And so basically, as you go higher and higher in dimensions, we are clearly able to see that negativity has higher errors when you do linear inversion compared to MBN. So that is the second prominent result of the manuscript. That is, MBN is more robust than negativity when you perform state estimation using Li. So that part is hidden here, and then particularly at higher dimensions. So is there a reason why this happens? Yes, there is a reason. If we recall correctly, negativity is built on negative eigenvalues. So it is built on negative eigenvalues, and linear inversion, on the other hand, also gives negative eigenvalues. So all the negative eigenvalues given by linear inversion is fed into negativity, and the errors add up. But in the case of MBN, it is not based on negative eigenvalues, because of which it can absorb some amount of errors in the state estimation when it's performed using Li. So in that way, MBN is more robust. So these are the two major results of the letter. And yeah, so basically we are approaching the end, and this is the summary of what we have discussed. So, firstly, I try to convince you that entanglement is wonderful and it's crucial to measure it. And we highlighted two important drawbacks of the existing entanglement measure negativity, which is bound entangled states, existence of bound entangled states or PPT entangled states, and the demand for accurate state estimation. And then we defined a new measure MBN based on IBM, improved block matrix criteria. And then we showed using examples, and which is practically expected, that MBN captures dynamics of various useful bound entangled states present in literature. And then we showed that MBN is more robust than negativity when the state is estimated using linear inversion. And the final takeaway message from this manuscript or from this talk should be that MBN is definitely not a replacement to negativity. It's not super. It's not superior to negativity, because there are entangled states that negativity can detect that MBN wouldn't. So definitely not. But it's a very suitable alternative when situations occur where you have bound entangled states in your system, or you end up with bound entangled states after a particular dynamics, or situations where you don't have the computational resources to perform MLE or other severe techniques, you are going to stick with linear inversion, but you still want to measure entanglement, then MBN is a very suitable alternative. Like they go hand in hand to negativity in those situations. And yeah, thank you for listening, and I'm open for questions.
Yeah, if there is someone who has any question, they may like just unmute themselves and ask the question right away.
Hi, Dharmaraj. Am I audible?
Yes, Karthik, you're audible.
Yeah, yeah, good talk. I have one doubt. In your modified block matrix, how do you decide the value of small m?
Okay, that's a nice question. So, deciding so that's where the authors give you freedom to play with m. M can practically be any positive integer, but for and improving n can like say for a particular value of m, say for 5, you might detect some states, and for a value of 10, you might detect some other states. So choosing the value of m is situation specific. You choose situations where, and also your computation also, because as you can see, as you increase m, you are scaling your matrix size. So huge m also means that you have to do a lot of computation, because finding a trace norm means you have to diagonalize the density, diagonalize the matrix. So choosing m is situation specific and also based on your computational power. So in this work, we have fixed m to 4, and it works pretty fine for us.
Okay, so it depends on the density matrix to which you
Yes.
are going to. Okay, and then on the slide number 17, I don't understand what is the y-axis counts mean.
Okay. Okay. So in that case, is the screen visible?
Yes.
So in this case, so it's basically a frequency distribution. So we had 1,000 states. Sorry, I didn't mention that. We had 1,000 states. So counts just means that how many states had that error. So here, if you see, it's around 120, means point one error was there for 120 states out of.
Okay, so
So
it's
it's
number
basically,
of states having that specific error.
yes, exactly.
Yeah, thank you.
Thank you so much for your talk. It was
Thanks.
interesting. I never, I mean, I work with spin qubits, but I never, read more about like entanglement in this much deep.
Okay.
Mhm. Is there any question anybody has? They may ask. You have a comment.
Yep. Oh. Thank you. I don't know how to pronounce. Is it Maja? I think so. Thanks.
Right.
So I have one more doubt. Actually, basically in the robustness study, you are trying to find out the inseparability of matrix. It is not a density matrix, right?
In a sense, yes, it is a quantum state. Negativity uses density matrix, and the our measure uses block
Block
matrix.
matrix. Okay. So actually, experimentally, what we construct is most of the time it is not a valid density matrix. We end up with a density matrix, Hermitian matrix with negative eigenvalues. So it's
Yes.
not a valid density matrix. So using in your study, you are trying to find out the inseparability of those matrices, right? Experimentally constructed.
Yes. In a sense, not exactly inseparable. Yeah, we are trying to measure the entanglement. Yes.
Yeah, that means inseparability. Yeah, right.
Yes. Yes.
Yeah,
That's right.
okay. It's interesting. Yeah. The first time I'm
Thank you.
Thank you for asking questions, Karthik. Is that Karthik? Right.
Yeah, that was.
yeah, yeah, yeah.
Thank you. It makes things more interactive. We can wait for one or two more minutes for people to think about the questions if they have.
Oh, or yeah, they can shoot me a mail or something also.
Yeah, they can write you mail, right?
Yes, 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 of course.
Yeah, you may find Dharmraj on LinkedIn, so it's very easy. He replies to the DMs. You can
Okay.
also get him.
Thanks for the advertisement.
So yeah, if there is any doubt still left, you may like connect with him through LinkedIn. That would be great. And because we are on time, like it's not that you finished very early or very late. It's fine.
Yeah.
So in the end, thank you so much, Dhamraj, for giving this wonderful presentation. And thank you so much, Karthik, for asking questions. Sorry, I forgot to turn on the mic. I mean, the camera. So wonderful, everybody. If anyone can, like, if you all can open your camera, we can take a screenshot, like, photo of everybody. Dharmaj, can you stop sharing your
Yeah,
screen?
yeah, please. Yeah, yeah. Sure.
Yeah. So if everybody can open their cameras, just a group photo. It's otherwise your name will pop up.
Yeah, I'm not sure how many are prepared for this, but
Hi, Ma. Hi, Mira. I will click the picture in like 3, 2, 1. So, Chang, Marja, you're left. Let me know. Should we wait for you or should we just go ahead and click the picture? I'll consider the silence as a sign to go. Okay, let's have a selfie. Got the picture. Thank
thanks.
you so much for joining in, everybody.
Yeah, thanks a
Yeah.
lot for the invite. Yeah, see you.
Yeah. See you. Bye bye.